Okay, in this lecture, we will continue what we were doing, developing the plane groups or the 2D space groups, you can say. So, in the last lecture, we had reached up till here, and we had the last thing that we did in the lecture was took a primitive rectangular cell and added a mirror plane to it to get the associated plane group. Now, today we will begin with taking a centered rectangular lattice and add to this a mirror. So, my centered cell would be lattice points at the corners and a lattice point in the center of the cell. Now, let us add a mirror to this. So, I put the mirror on one of the edges and putting the mirror vertically. The translation would bring the mirror here, and we have already seen, and also there is a centering translation as well. So, a mirror will pass through the middle lattice point as well. So, this is how the group would look like. Let me put some motifs also in this. So, I put a right handed motif here, the mirror reflects and makes it left handed. Translations will take both the motifs, right handed and the left handed, to every lattice point. And there is also translation to the centered lattice point as well, and that would put the motifs out here. Now, let us consider, let us say that this is motif number 1, this is motif number 2, and the translation took it to motif number 3. So, I go from 1 to 2 through a reflection operation, then 2 to 3 via a translation operation, which is nothing but, if I call this as this is my A vector, this is my B vector, then very clearly the translation vector which will take the motif from 2 to 3 would be half of A plus B. So, now the question we ask is, how do I go from 1 to 3, or what operation, what symmetry operation should take me from 1 to 3? Because after all, for it to be a group, for it to be a symmetry group, there are certain rules according to the group theory that have to be followed, that we discussed much earlier on. Now, one of the essential rules is closure. Therefore, a combination of 2 symmetry operations should give me a third symmetry operation. So, if you look at 1 and 3, 1 is a right handed motif and 3 is a left handed motif. So, certainly no kind of translation can take it there, no rotation can take it there, because rotation and translation will not change handedness. Therefore, there has to be a reflection operation of some kind, but very clearly I really can't put a mirror plane inclined, because if I try to put the mirror plane inclined, I will destroy the entire symmetry of this set of symmetry that is there in the rectangular lattice. Therefore, we have to look for a kind of operation that we have not seen as yet. So, let us try to figure this out. I put this in a separate diagram. So, what I actually have, if you think about it, that I have a mirror and a translation. This is my centering translation, this is my essentially my translation T. Now, if I draw this separately, so I have a mirror here translation T. Let me put now couple of motifs. So, let us start with my asymmetric motif that I have used very often. Let us say this is at a distance of delta from the mirror plane. It reflects into a left-handed motif, and this left-handed motif will also be at a distance of delta from the mirror plane. Now, the translation operation, so this is my motif number 1, this is motif number 2, which is left-handed. The translation operation T would take this motif somewhere here, and the handedness of the motif will not change, and this becomes my motif number 3. So, the question again I am asking is, how do I go from 1 to 3 in this case? Let me just enlarge this drawing a bit, otherwise it will become very congested. So, this is motif number 3. Now, let us go back to my translation T out here. I can break this translation into 2 components. One component is the translation perpendicular to the mirror plane, I will call that as T perpendicular, and the second component is a translation which is parallel to the mirror plane, I will call that as T parallel. Now, in the same way, this translation that I have done to take it from 2 to 3 will be broken up into the same components. So, this is T perpendicular and this is T parallel, and if you further notice, motif number 2 was at a distance of delta away on the left side of the mirror, and therefore, this distance should also be delta. Now, motif number 1 is already delta away on the right side from the mirror. Just think about it that if we draw after all I have to change the handedness, 1 is a right handed and 3 is a left handed. So, I need to change the handedness. So, what can I do? I can try, suppose I put a mirror. If I put a mirror, motif number 1 will be reflected with the handedness changed, something like this, and it will be directly below motif number 3, but it will not coincide with motif number 3. How can I make it coincide? I can make it coincide if I translate it, I do not leave it there, but I translate it up, then it will coincide. And how much of a translation I need to give? I already know that the amount of translation I need to give parallel to the mirror plane is T parallel, and therefore, I should, in fact, this is how things will work. Motif number 3 gets reflected first, but it is not left there, but it is translated up by T parallel, then there will be self coincidence. Now, with this, basically what this means is that this is not an ordinary mirror anymore. It is, and I will draw a new kind of mirror which will be shown as dashed line, and I will label that as G, G that stands for glide. So, this is what is called as a glide reflection, and basically a glide is a 2-step operation. First, reflection, and the second step translation. Now, since there is translation involved, glide is not a point operation or not a point symmetry. If you recall, a point symmetry will at least have one invariant point, but whenever there is translation, then there are no invariant points. So, a glide operation cannot exist in point groups, it will always exist in plane groups or space groups. So, now where does the glide come in this? In my plane group of centered rectangular in which I have added a mirror, well, clearly this is the mirror and this is the translation which is at an oblique angle to the mirror, not at 90 degrees. So, therefore, the glide operation must come somewhere here. By symmetry, obviously, there would also be a glide at this point also. So, as far the plane group is concerned, we have completed the construction, but there are a few more things. Where I have put this glide? So, if we go back to this diagram, where is this glide located? Glide is located exactly at half the perpendicular translation or the midpoint of the perpendicular translation component. So, basically what I am saying is that this is T perpendicular by 2, this is T perpendicular by 2. And where is the T perpendicular in the plane group diagram? Well, this is basically B by 2. So, if I look at this, this is my perpendicular component and A is the parallel component. So, this is perpendicular and this is parallel. So, location we know now, and I also want to know. So, I will just so let me write this combination down first. I have an operation of reflection followed by translation. Then the symbol that I use for glide is again it is a kind of reflection. So, we will stick with sigma, but we will put a subscript tau, and it is located at T, the perpendicular component, divided by 2. So, I should also express this like this: T parallel, or rather the magnitude of T parallel is the two vectors, the perpendicular vector and the parallel vector. It is a parallel vector which is called the glide translation. So, tau is essentially the translation component, glide translation. Now, we want to also try to figure out what is the magnitude of the translation, which means what is the magnitude of T parallel. So, let us try to understand this through another diagram. And let us say I start with a right handed object, I reflect and then translate, and this becomes a left handed motif. Again reflect, change of handedness and translate to a new position, but this object is not to be kept here. Again reflect, translate, reflect, change in handedness but I do not leave the object here. This is how the pattern will look along the glide plane. And how much I translate every time? I translate by a distance tau. Now, let us look at what are these distances. This is clearly 2 tau. Again, between this object and this, so on the right hand side, this is 2 tau, and this is a right handed object. By mistake I have put it as left handed. If I were to reflect it again, translate, I come to a left handed object on this side. So, what are these distances out on this left hand side now? You will see this is also 2 tau, this is also 2 tau. Very clearly, 2 tau represents, if tau is a translation vector for the glide translation, then 2 tau is the lattice vector along the glide plane. And what is the magnitude of this lattice vector? This is the minimum, and this has a minimum lattice vector, that is minimum magnitude. So, between lattice points, basically the adjacent lattice points which are running along the glide plane. So, an important conclusion that follows is that the glide translation is exactly half the lattice translation along the glide plane. So, glide translation tau. Now, coming back to the plane group diagram, how much is the glide translation? Well, very clearly the glide translation is, which is nothing but half a. So, it is exactly half the lattice translation along the glide plane in the plane group as well. So, this we have. Let us just also look at what would be the matrix for such an operation, which is a combination of reflection and translation, and actually turns out to be quite simple. So, the glide matrix let us start with the mirror plane, follow it up with a translation, and just this is my, let us say, the x direction, this is the y direction. So, reflection followed by translation gives me sigma tau, where tau is equal to t parallel and located at half the perpendicular component. In matrix form, the reflection operation, so my mirror plane is normal to the x axis, basically the mirror plane is in the yz plane. For that, the matrix is bar 1 0 0 0 1 0 0 0 1. And for the translation operation, we have already seen that what would be the translation matrix in homogeneous coordinates, 1 0. So, the perpendicular translation, so I should just take the two components here, this is t perpendicular, this is t parallel. So, 1 0 t perpendicular, 0 1 t parallel, 0, 0, 1, and just multiply the two matrices. The result would be bar 1 0 t perpendicular 0. So, this is minus 1 0 t perpendicular 0 1 t parallel 0 0 1. This is my glide matrix. Now, how do I interpret this? Because I have this t perpendicular and t parallel components are there. Let us compare with the mirror matrix. Now, before I proceed, I should know where is my glide. Glide is at t perpendicular by 2. So, compare with mirror, mirror located at a comma 0, recall. So, this is sigma at a comma 0, and this matrix, remember, we had derived it as minus 1 0 2 a 0 1 0 0 0 1. If you compare the two, very clearly the mirror is telling me that t parallel is equal to 0 and t perpendicular should be equal to 2a, or essentially basically I am saying that a is equal to t perpendicular upon 2. So, if I put, so whenever I put t parallel is equal to 0 in the glide matrix, basically the glide becomes a pure reflection. Then it becomes a point symmetry because the translation is gone. Now, one last thing before I complete this lecture is, can t parallel be a lattice translation? You can pause the video here and give it some thought. Try to draw the glide plane along with the motifs, taking t parallel to be a lattice translation, and then try to come to a decision whether t parallel can be a lattice translation for glide. Here it goes. This is my glide. I start with a right handed motif, go up, glide translation, go up, handedness changing accordingly. And so on. I can keep creating this pattern till infinity. And this is basically my t parallel or tau. So, here also this is t parallel or tau. Now, I am saying tau or t parallel is a lattice translation, which means the lattice translation symmetry also has to be imposed. And if I do that, then the motif here, for example, would be taken to this location. Similarly, this motif will be taken here, this motif will come here, and this motif will come here. And if you look carefully at this diagram, this has become a pure, mirror. So, therefore, essentially it means that tau can be 0, then also it is a pure mirror in the glide matrix. If tau is a lattice translation, then also This is no longer a glide matrix, but becomes basically a pure reflection matrix. With this, I will close this lecture. Thank you.